In the past two videos, we have established that the imaginary number I is defined as I squared equals -1, but we can think of I as being equal to the square root of -1. We can multiply a real number by an imaginary number to get another imaginary number, and if we multiply imaginary numbers with each other, we get integer powers of I listed here, and these powers repeat in cycles of 4. Here are all the concepts from the previous two videos, which you can review, or watch the previous two videos if you need more information. So what happens if we add a real number with an imaginary number? What results from this sum is a complex number. A complex number is a number in the form a plus bi, where a and b are real numbers, and I is the imaginary number I, as defined earlier. Complex numbers are usually represented with the letter z, so here we are saying that the complex number z equals a plus bi. So an example of a complex number is something like 1 plus I. We can see that this is the sum of the real number 1 and the imaginary number I. Another example is something like 2 minus 3i, which is the sum of the real number 2 and the imaginary number -3i. This number is also in the form a plus bi, where a equals 2 and b equals -3. When we have a complex number in the form a plus bi, we say that a is the real part and b is the imaginary part. So in this example, 2 minus 3i, the real part is 2 and the imaginary part is -3. Let's consider how we could add two complex numbers. If we have a complex number z1 equals a plus bi and another complex number z2 equals c plus di, where we use the coefficients c and d, then z1 plus z2 is equal to a plus c plus b plus d times I. This basically means that you combine like terms and add up the real parts from the two complex numbers and then add up the imaginary parts separately to form a new complex number with the summed real and imaginary parts. So if we have something like z1 equals 3 plus 2i and z2 equals 4 minus 7i, then z1 plus z2 equals parentheses 3 plus 2i plus parentheses 4 minus 7i. We can get rid of the parentheses and rewrite this expression as 3 plus 2i plus 4 minus 7i, and then combine like terms. If we look at the real terms, 3 plus 4 is equal to 7, and if we look at the imaginary terms, 2i minus 7i is equal to -5i, so the entire sum is equal to 7 minus 5i. So this was somewhat implied when we went over the process of the addition of complex numbers, but addition of complex numbers is commutative and associative. Commutativity, as you may know, means the order of the terms in the sum doesn't change the value, and associativity means any rearrangement of the parentheses doesn't change the value. So basically, it's the same properties of addition involving real numbers, and this is fairly intuitive. Another thing to note is that real numbers are also complex numbers. Since a complex number is in the form a plus bi, we can think of any real number as a plus 0i, where the imaginary part of the complex number is 0. Imaginary numbers are also complex numbers, since we can think of any imaginary number as 0 plus bi, where the real part is 0. So this means sums of imaginary numbers, or sums involving both real and imaginary numbers, are also commutative and associative. These are just some things to keep in mind going forward. Subtraction of complex numbers is pretty much the same, except you need to find the difference of the real and imaginary parts of the two complex numbers instead of the sum. The process still involves combining like terms, just like with the addition of complex numbers. So if we have something like z1 equals -4 plus 3i, and z2 equals 5 minus 2i, then z1 minus z2 is equal to -4 plus 3i minus parentheses 5 minus 2i. Just like with the addition of complex numbers, we remove the brackets, but since we have a minus sign before the second parentheses, we need to distribute the negative into both terms. So this expression becomes -4 plus 3i minus 5 plus 2i. If we combine like terms, then this simplifies to -9 plus 5i, since -4 minus 5 equals -9, and 3i plus 2i equals 5i. So before I get into the multiplication of complex numbers, I would like to talk about the multiplication of imaginary numbers and the multiplication of a real number with an imaginary number. You should note that multiplication of complex numbers are commutative and associative, and this is why the formulas I am about to present can work without having to worry about the ordering of terms and parentheses. So if you multiply two imaginary numbers, ai and bi, you end up with ab times I squared, and since I squared equals -1, this just turns out to be ab times -1, which equals negative ab. So the product of two imaginary numbers is always a real number. So for example, 2i times 3i is equal to -6, since we multiplied the real numbers 2 and 3, and then multiply that with I squared, which equals -1, so the entire product just turns out to be -6. If we multiply a real number a with an imaginary number bi, the result is just abi. So basically we multiply the real number onto the real coefficient before the imaginary number, and the I stays the same. So if we have something like 2 times 3i, we just multiply 2 by 3, which equals 6, and the I stays the same, so the result is 6i. So now let's get into the multiplication of complex numbers. If we have z1 equals a plus bi and z2 equals c plus di, then z1 times z2 is equal to parentheses ac minus bd plus parentheses ad plus bc times I. This formula is derived by taking the two complex numbers a plus bi and c plus di and expanding out the product a plus bi times c plus di using the distributive property as shown on the right-hand side. The distributive property also applies for complex numbers, which is why this method works. After the expansion is done, we simplify the expression with four terms by rewriting I squared as -1, and then isolating the real and imaginary parts to form a new complex number. The result of this process is the formula presented for z1 times z2, but you don't have to remember this formula if you remember the process for multiplying two complex numbers. So let's say z1 equals 3 plus 2i, and z2 equals 5 minus 3i. Then z1 times z2 is equal to parentheses 3 plus 2i times parentheses 5 minus 3i. If we apply the distributive property as we normally would for any expression, then this is equal to 3 times 5, which is equal to 15, plus 3 times -3i, which equals -9i, plus 2i times 5, which equals plus 10i, plus 2i times -3i, which is equal to -6i squared. Well, I squared is just equal to -1, and -1 times -6 is just equal to +6, so this expression simplifies to 15 minus 9i plus 10i plus 6. If we combine like terms, then 15 plus 6 is equal to 21, and -9i plus 10i is just equal to I. So this product is just equal to 21 plus I. So, as stated earlier, multiplication of complex numbers is commutative and associative. So if we have two complex numbers, z1 and z2, then z1 z2 equals z2 z1. And here I am just writing the product without the multiplication sign, but it means the same thing. Also, rearranging parentheses in any product of complex numbers doesn't change the value, which is what associativity means. And of course, real numbers and imaginary numbers are also complex numbers as stated earlier, so these formulas apply to real and imaginary numbers too. The distributive property also applies to complex numbers, so z1 times parentheses z2 plus z3 is equal to z1 z2 plus z1 z3. These properties were all implied when I went over the multiplication of complex numbers, but we formally state them here. So before getting into the division of complex numbers, there's another thing I need to talk about, and that's the complex conjugate. Suppose the complex number z equals a plus bi, then the complex conjugate of z, which is written as z bar with a bar on top of the letter z, equals a minus bi. To find the complex conjugate of a complex number, you need to keep the real part the same and invert the sign before the imaginary part. So for example, if we have the complex number z1 equals 3 plus 2i, then z1 bar, which is the complex conjugate of z1, is equal to 3 minus 2i. Notice how we simply inverted the sign before the imaginary part from positive to negative. If we have something like z2 equals 4 minus 7i, then z2 bar is equal to 4 plus 7i. Since the original complex number had a negative sign in front of the imaginary part, after we invert the sign, the conjugate would have a positive sign in front of the imaginary part. So let's consider what happens when we multiply a complex number with its conjugate. So suppose z equals a plus bi. Then z times z bar is equal to a plus bi times a minus bi. Since the product is in the form where we can use the difference of two squares formula, this just equals a squared minus bi all squared. And this is equivalent to a squared minus b squared I squared. And since I squared equals -1, this equals a squared minus b squared times -1, which is just equal to a squared plus b squared. Therefore, we can conclude that z times z bar is equal to a plus bi times a minus bi, which is just equal to a squared plus b squared. And this is a formula that's important for division of complex numbers. And notice how the result of multiplying a plus bi times a minus bi, which are two complex numbers, is just a real number, a squared plus b squared. Alright, so now we can get into the division of complex numbers. Let's say we have a quotient like 4 plus 7i divided by 3 minus 2i. We would like to rewrite this in the standard form a plus bi, where a and b are both real numbers, so we need to get rid of the imaginary number in the denominator. The first thing we need to do is multiply both the numerator and denominator of the fraction by the complex conjugate of the denominator to make the denominator real. The complex conjugate of the denominator, 3 minus 2i, is 3 plus 2i, so we need to multiply both the top and bottom parts of the fraction by 3 plus 2i. The reason we do this is that the denominator is now 3 minus 2i times 3 plus 2i, which is in the form a plus bi times a minus bi. So we can use the formula a plus bi times a minus bi equals a squared plus b squared, which is just a real number. This means the denominator is a real number, which is what we want. If we use the distributive property to expand the numerator, it becomes 12 plus 8i plus 21i plus 14i squared. We can simplify the denominator using the formula I just mentioned. So 3 minus 2i times 3 plus 2i is equal to 3 squared plus 2 squared, since in this case a equals 3 and b equals 2. So a squared plus b squared equals 3 squared plus 2 squared. Since I squared equals -1, we can simplify the numerator to 12 plus 8i plus 21i minus 14, and the denominator becomes 9 plus 4. If we combine the real and imaginary parts from the numerator simplifies to -2 plus 29i, and the denominator is equal to 13. If we distribute the division, this is equal to -2 over 13 plus 29 over 13i. And now this is in the form a plus bi, which is the standard form of complex numbers. So here's the formula for division of complex numbers, but if you remember the process, you don't have to memorize the formula. The proof is shown here, and it's essentially the same process for the example that I covered, except it's done with unknown coefficients. So the last thing I want to cover in this video is the absolute value of complex numbers. You may recall that for real numbers, it's thought of as the distance of a number from 0, and the same idea carries over to complex numbers. So if z is the complex number a plus bi, then the absolute value of z is equal to the square root of a squared plus b squared. This formula calculates the distance of the complex number from 0, but it'll be more clear why this formula makes sense when we cover the complex plane, which is the geometric representation of complex numbers. You can think of it as the two-dimensional version of the number line for real numbers. So if we have something like z1 equals 5 plus 3i, then the absolute value of z1 is equal to the absolute value of 5 plus 3i, which equals the square root of 5 squared plus 3 squared, since in this case, a equals 5 and b equals 3, and this simplifies to the square root of 25 plus 9, which equals the square root of 34. If z2 equals 3 minus 4i, then the absolute value of z2 is equal to the absolute value of 3 minus 4i, which equals the square root of 3 squared plus negative 4 all squared, since a equals 3 and b equals negative 4. And this simplifies to the square root of 9 plus 16, which equals the square root of 25, which equals 5. The absolute values of a and b, which are 3 and 4, along with the answer 5, form a Pythagorean triple, which is why the absolute value of z2 turns out to be an integer.